and then we have to, like, I guess, try to change the grade after the semester ends. But yeah, so just keep that in mind. All right. So okay. So anyway, so that's enough for that. Any questions before I get started? Okay. So we will continue our next step in linear algebra. So now, from now on, this stuff that we're going to be talking about, it's going to get quite a bit more abstract. However, I will always refer to examples so you guys will understand what I'm talking about. So in the first three chapters, we've mentioned, what a vector is, and I mean, you guys already know what a vector is in the sense of, maybe you've seen it in physics class or any other like STEM class. So we're basically going to take that concept that you know and generalize it even more. So you'll no longer be thinking of them as just arrows with directions now. We're going to start thinking of them in different ways now. All right, so just to start, so we now discuss in detail what a vector really is. Okay. So we will give formal definitions of the vectors we are currently familiar with. And the vectors we're familiar with is, well, vectors in Rn, right? So these are going to be vectors in Rn. Okay. So let's give our first. I mean, you guys, again, some of the stuff you might be, it might be redundant, but again, we're gonna build up what it means to be a vector here soon. So first, let's give out a definition of something you've already seen before, right? So the set Rn is the set of all ordered n tuples. So what I mean by n tuples, it just means like a two tuple just means you have a list of two things. Three tuple just means you have a list of three things. N tuples means you have a list of n things. So of real numbers. So we denote this set to be, again, so this list is like x1 all the way to xn. So n things, and what those things are real numbers in our case. Okay. So I mean, so how we've been using them is, again, we take elements out of the set, we've been using them as vectors, which is a true statement. However, I never really said what it meant to be a vector. So so we usually denote this list as, say, x1, like this, right? So we've been using this notation all the time. Okay, so far this is the only thing we know, right? So we have this set of list of things, and those things are real numbers in this list, right? So let's see. So again, we've worked with these things before, or structures before. So let's give an example, n equal 2, right? So if we give an example of n equal 2, so for n equal 2, we have R2, right? And in R2, I mean, this thing before, you guys worked with maybe in physics and all that stuff. So we can visualize this as arrows in the plane, right? So we can visualize these as arrows in the plane. So again, I mean, you have your y and x, and then if you have a vector that's in R2, it's usually done like this. You know, let's say this one equals, I don't know, 1, 1. That just means this component right here is 1, and this component right here is 1, right? And in physics or engineer or just STEM in the general, and let's just say physics, because we've seen it the most. You characterize a or this vector as with, well, I guess you can say with its length and direction, right? Meaning this direction references this angle theta, you can say. So okay, this is how we've always thought about them. Yeah. So for R3, you would need 3 axes, right? You would need an x, y, and z, but you still characterize them as you still would characterize the vector as terms of its length and the direction it's pointing in, right? But yeah. So I mean, so again, this is all stuff we know, right? We've dealt with these. I've been using them. You probably used them even before this class. So let's now talk about some of the things that we, I guess, not say take for granted, but we just do it without really thinking about it. But we're gonna formalize it here, and there's a reason I'm gonna be formalizing it, because all of this is just gonna build up to what it means to be a vector. Okay. So again, so we will learn a more general definition of a vector. Okay, but first, let's talk about some things that, again, we might have taken for granted, and that is like this stuff right here. So let's define something. So let's say B and U be like these list of things, right? So again, we know they're vectors, but let's just say they're the list of things that we talked about. And let's say we take a scalar lambda from or a real number from R, okay? So again, all I've said so far is that this Rn is a set of all n tuples or list of things, right? I haven't said anything else about it. So a natural thing you might ask is, again, again, you might already know this, but again, so before this whole thing, it's just say we don't know any of this. How do we consider two vectors to be the same in Rn with these list of things? Well, we say, let's say U with components U1 all the way to UN, and V are equal. If each, again, and the most natural definition would be if each component is equal to the other one, right? So each one of these has to be equal, right? In order for the vector as, or the list as a whole to be considered to be equal. Another thing, okay, so now that we know what it means to be equal, how do we define, maybe something called addition between vectors? Because remember, uh, for real numbers, we know what it means to add. But if for a list of numbers, what does it really mean to add? And I mean, we've already been doing it. We've added them component wise, but again, we have to have these meanings to these structures before you even advance. So that's why we're doing that's why we're going through all this. So we say we add, let's say U and V, component wise. Meaning if I wanted to add two of these lists, right, U and V, how I would add them is you would take the lists and you just add them component wise, meaning you'll just add literally each component like this. Right. Okay, so this is now we get meaning of what it means to add to this. And then last but not least, what does it mean to multiply a number or a scalar with the list? So we multiply by a scalar, and that's in this case lambda, to the list V component wise. So lambda V is going to equal to lambda V1 all the way to Vn. And then you just literally multiply each one of these by each component, right? So again, I mean, we do this again. So I just want to point out, we do have a notion of that. We know what it means to multiply real numbers, right? This notion right here, we didn't know until we defined it to be this. Okay, so I'm just trying to make it clear to you that this multiplication is not the same as this one being that's happening here. Okay, this multiplication, we defined it to be this way. Okay, so again, keep these thoughts in your head. Yeah, I can shake it. When you're like thinking of these, because so this is where you guys are gonna do like proofs for vector spaces, and I mean, you might have to like think of it this you might have to think of it this way. It's okay. I shrunk it. Okay, and then finally, now we denote this 0 with an arrow overhead. That's the list with every entry being 0. Or we can call it as the 0 vector. Or all entries are 0. Okay. Okay. Okay, so again, okay, so now we gain meaning to addition, multiplication, and then we gave notation to the 0 vector, right? Or the 0 list. Now I'm going to go through 2 theorems, and again, these theorems might seem very obvious, but again, the obvious part is not that. It might be obvious because of how we've always worked on it, but again, it's just think of it as a new result with the new meaning that we gave to vector addition or list addition, right? So Let's talk about this first theorem. So let U, V, and W be Rn, and alpha and beta be real numbers. Or we call these again scalars. And I'll tell you what it means to be a scalar as well. So we have these two things. Well, we actually have like 10 things. So again, this might be obvious, but just think about it for a second. So if you add to say two lists or two vectors together, right, with the meaning we've given them in the previous definition, this first property is true. So adding two vectors or two lists gives me another vector in that same space, right? You can think of it. So like, for example, if I add the vector 1, 2 with 2, 3, I add them together, it gives me the vector 3, 5, right? It's still a vector that's in R2, right? So you see how I added two different things in R2, and it gave me a third thing that was also in R2, all right? So what this is called, if you have this and whatever the operation you define to be, and you like stick them together, and it still stays in that same space, in this case being in R2, this is what's called closure under that operation. In this case, it's closure under addition, okay? So this is closure under addition. Okay. Second, we also know that our lists commute, and they commute because real numbers, if you do the addition, how we define the addition, we can commute real numbers, and therefore it also commutes, the list commutes. So we have this commutative property. We also have that any vector or list plus the zero vector or list is going to give me back that vector, okay? So this is called something as the additive identity. We also have association, meaning if I add the first two vectors together and then add the third one, that's the same thing if I add the last two and the first one. So like this. So this is, again, that's called association. B, every vector or list has something called the additive inverse, meaning U plus, and the additive inverse of this is just the minus of it, will give me the zero vector. So this thing is called the additive inverse. We also have that the scalar times U. So how we define the meaning of some real number being multiplied by a vector, this is also a vector or list in Rn. So this is, so just how the first one is closure under addition, this is called closure under scalar multiplication. Okay. So now We also have the distributive property for these. Distributive. And that also goes for this part right here. Alpha plus beta on U. It's also just alpha U plus beta U. So both of these things are called the distributive property. So that goes for both of these. We also, so two more. We also have this. So we can associate scalar multiplication as well. And then last but not least, one, that real number 1 times U is just going to give me back U. So this is called the multiplicative identity. Okay, so again, so why did I even list out all these maybe seemingly obvious things? Well, because for real numbers, they're very obvious, yes. However, when we talk about different objects under a different operation, it might not be so obvious that these things hold, okay? Yeah, 1 times U equals U. Yeah, it's 1 times U. And this is the scalar multiplication we defined on the list, yes. So, by the way, if you guys have ever heard of the word groups, like maybe in physics or something like that, or that, I mean, all this stuff like pretty much defines Rn to be a group. But anyway, so yeah, so again, there is a punchline to this, so don't worry, we're almost to that part. Okay, so let's go to the second theorem, 4.1.2. So let U, or say V, be in Rn, and alpha be in R. We also have this, the additive identity is unique. So what do I mean by that? So if you go back to the previous theorem, the additive identity in that case was 0, right? So U plus 0 gives me U again. So 0 is the additive identity for U. What this is saying is that how do I know there's not another number or vector in there that is also like, that gives me U. So let's say that 0 wasn't 0. So let's say so I guess you can say in other words, so maybe you can say that is if say V and take another additive identity, say it was U is equal to V, right? Then U has to be 0, right? So no matter, so that's the only one in there that has this property, is what it's saying. Secondly, let's see, the additive inverse is unique. Again, that is if V, so again, the additive inverse for the one we did, the one I showed you in the last theorem. So if V was a vector, its additive inverse would be negative V, because V plus negative V gives me 0, right? So that, what this is saying is that the only additive inverse for V has to be negative V. There is no other such vector. So again, so that is if V plus W is equal to 0, then W has to be minus V, okay? We also have 0 times any vector is 0, the 0 vector. And this is being the scalar, not the vector itself. And a scalar times the 0 vector is just the 0 vector as well. Then last but not least, if alpha times V is equal to 0, then alpha is 0 or V is 0, the vector. Yep. Okay. Okay, so let's do one proof, just to get you like warmed up for the stuff that's gonna come. So let's prove the first one. Okay. Let's prove that this additive inverse, additive identity is unique, meaning in this case, so the additive identity was this part right here. So this part, this thing is right here is the additive identity. 0 is the additive identity, right? So we're going to prove that 0 is the only one. So how do we do this? Well, suppose there was another vector that did the exact same thing. So say by way of contradiction, suppose there was another vector, say W, that is not 0, such that it also did V plus W is equal to V, okay? Suppose that this vector existed. Okay, so now let's try to do some stuff that we can do. Okay, so from here, what I'm gonna do is I'm gonna let's add negative V to both sides of this, okay? So let's do V plus W and then plus negative V. So I'm adding this part to both sides of the equation. So let me just put it in a different color. Is equal to okay, perfect. Okay. So now let's use the fact that if you go back in this theorem, let's use the fact that vectors can commute and associate. So I'm going to move this V and W around to where I have just W W factorial. Oh yeah, does not equal. Yeah. Does not. Yeah. So this does not equal 0. So suppose that this did not equal 0, the 0 vector. Yeah. Okay. So now let's associate and make these two vectors together. So according to my theorem over there, I know that this thing right here is 0. So this is just going to be equal to 0, right? With this part. According to the theorem that I stated last time, right? Come on. Okay, so no. Okay, so now I'm just left with that. Okay. However, I also know by that theorem that this is also 0. So now I get that W is equal to 0. But I started assuming that it was not 0, so that you have a contradiction. So that means that there is no other vector that can be 0. So a contradiction. So 0 is the only additive identity. Okay. So this is just a, I guess, a preview. It won't be, I guess, like this, but you guys will be doing vector space proofs. It's not hard. It's just it can, like I said, I'll break it down to where you just check a bunch of things on the list. But yeah. So okay, perfect. Okay, so now let's get to the punchline of this whole thing, or the entire thing I was trying to like do here. So let's go on to the next section. Where is it? Here it is. So now we are finally ready to define what it means to be a vector in a more general sense. There's still more general definitions out there, but at least we have this. So again, so in order to define what a vector is, we first need to define what a vector space is. And to define what a vector space is, I'm first going to define what a field is. So, but we won't, like, you won't have to know what a field is. We'll just take R to be our field, but it doesn't hurt to know. So we have always been taking scalars from R, right? This entire time we've just been taking numbers from R and then multiplying and whatever, right? So in general, we don't have to do this. We can take scalars from something called from a arbitrary field, something called a field, and we denote it like this. It's just a bolded F. So let's give a informal definition of a field. And again, I'm just gonna, and then after I give the definition, I'm just gonna summarize it in layman terms, and you'll be good to go with that. So, informal definition. A field is a set denoted as bolded F, right? So again, a set is just a collection of things containing at least two distinct elements, say 0 and 1. Now, this isn't the 0 and 1, you're like real number 1 or real number. This is a different 0 and 1, okay? So we just label these things called 0 and 1. And then, okay, so this field has this thing called a 0 and a 1 that does exactly what you think. That you add a number to, you add the object to it, you get the object back. You multiply this 1 to it, you get the object back, okay? So along with a operation called addition. And again, this addition is not the addition you think of, because it's not. So again, all this will be made clear here in a few minutes or so. And multiplication. And multiplication satisfying, well, satisfying everything like what you would think a real number does. Okay, so so if you have alpha plus beta, this equals beta plus, so it commutes. So for all alpha and beta in this field, this thing called a field, the things commute under this operation of addition. size. And I started at 2, so that should be a 1. The stuff that is in this field also has a distributive property. I mean, associative property. I should probably put one more thing here. Equals alpha. Lambda plus 0. So this thing that's called 0, again, it's not the 0 that you would think of as like a normal 0, but this 0 under this operation gives me back the object. There exists a alpha 1 in the field such that alpha plus alpha 1 is equal to that 0 thing that we called. There also exists an alpha 2 in my field such that when you multiply under this multiplication operation we have, it's the number 1, or what we called the number 1. And then 6 lambda times alpha plus. So we also have distribution here. Okay, perfect. Okay, so this is so I took basically the concept of the field and I basically tried to like condense it into something that is understandable. But yeah, so you can just think of this thing, a set of things where you have this thing called addition, multiplication, and this thing called a 0 and a 1, and it satisfies all this. That's what a field is. Now, if you take the field to be real numbers, obviously we have a 1 and a 0 in our notion of addition and multiplication is how we define it, and it satisfies all this, right? Any real number plus 0 is that number itself. Real numbers commute, real numbers associate. If you have a number alpha, the number that you get, I guess, for this one. So if you have a number alpha or a real number alpha, the alpha 1 becomes just negative alpha, and that gives you 0, and so on and so forth. So again, that's what it is to be a field. In this class, so hold on a second. So yeah, so throughout this class, we will take our field F to be, sure. So number 5, yeah. So it's like so like for the real numbers, right? So let's say I took the number 2 from the real numbers. Does there exist a real number, I don't know, alpha 2 such that 2 times alpha 2 is equal to 1? Yeah, right. I mean, it's just going to be 1 over 2, right? So that's what that's saying. So in this field, there exists this element such that you have this property, and real numbers obviously have it. And no matter what real number I take the number 5, then the number that I have to take to multiply 5 by to get 1 is 1/5, right? So that's what number 5 means. There's a multiplicative. Sorry, it's not the multiplicative identity. It's a I guess the multiplicative inverse is what it is, right? You take the number, multiply by this inverse, it gives me 1. This, yeah. So distributive, yeah, this part right here is distributive, number 6. So again, it's just like like real numbers, right? Take 2 times 5 plus 10. I can distribute the 2 in, and it'll give me the same answer, right? So the field in general has this property as well. So again, you guys won't have to think of this in this general, because I'm going to take F to be R anyway. So, but like I said, I thought it's still a good idea for you guys to know this, because again, vector spaces don't always just have to be arrows, and you'll see that in this class, you'll see that there are always going to be arrows with real numbers, with scalars coming out of real numbers. Okay, so yeah, so I mean like so for example, I mean like let's see, what's a good example? So like for example, functions, right? What does it mean to add two functions like this, right? Well, in college algebra you define it to be, well, first in order to uh, let's see, in order to define what it means to add two functions together, you defined it to be, okay, first evaluate x on f and then add it to g or on x. So this isn't the same addition that we have here, right? This addition that we have on the left hand side is not the same as the one on the right hand side. This is what I mean by that. Or like for example, another one. Let's say I defined the addition between a plus b. Let's call this addition like, I don't know, like I don't know, like a plus a or something like that. Let me define this to be a plus b over 2, right? So this addition right here is different from this one up here. So this one's a normal one, you know. This one I defined it to be completely different, right? So now whether or not this addition satisfies the properties that are listed here, that's to be seen, right? I don't know, you would have to check it. But that's what I mean. So the addition that I'm talking about here isn't the same as the one in real numbers. It can be whatever you define it to be. And you'll see it very quickly right now, because this is why I'm saying that this is going to get pretty abstract and pretty quickly. You'll see that vectors, again, aren't always real, just lists of numbers. They can be functions, they can be matrices, they can be just like smooth functions over but yeah, so like they can literally be anything, but you still need to have that notion of addition between those two elements, okay? Between those elements. Okay, all right, so here is finally where you guys have been wanting to see. So let's define what it means to be a vector. So a vector space. So I'm gonna use this notation, and again, I'm gonna explain the notation. So the vector space is the triple. So in order to have a vector space, you need these three pieces of data. So you need a set V, you need an addition, however you define this addition, and you need a multiplication, okay? You need these three data, or sorry, I guess you can think in computer science, like you need these three inputs to get a vector space out. You need a set, you need an addition on the set, and a multiplication on the set, okay? So again, so let me be a little more precise. So V is a set, plus is the addition, and the dot is the multiplication. So just how I explained it, right? Okay, so we say a vector space is the triple V plus times over a field F, and again, this is just real numbers for us, if the following hold. So one, if you take two elements, so let's say if you take two elements from my V, and I'm going to denote them like this. If you take two of these in my vector, or in my V, in my set V, U plus under this addition plus V is also in V. Again, this means this is closure. Two, your elements have to commute under this addition. So commutative. Three, you have your elements have to also associate. Okay, associate. 4, there exists a 0 vector. There exists a 0 denoted as 0 in this set V, such that for any element you take in my V, V under this addition with this 0 is going to give me V. Okay. 6. We're almost done with this. So if you take a scalar from my field and you call it alpha times this u, so like, I guess maybe better yet. So if alpha is my field and V is in my set V, then alpha times under this multiplication, V also has to be in V. Okay, so it's closed under the multiplication. 7. Size. We also have distribution. Where is 5? Oh yeah, my bad, I missed it. Yeah, hey, I'll get it right now. For any alpha in the field. So here's 5. 5 for every element in my V, there exists a vector in V such that, or denoted, I guess we'd say denoted as negative V. Such that V, or oops, I used, let me just change this, oops. Say that's V. So V plus minus this V is 0. Okay. Let's make this a little bit more tiny. Okay, so after this, we're pretty much done with the class, but so let me just finish writing everything out. 7, 8, alpha plus beta times u is equal to alpha u plus beta u, 9 alpha beta u is equal to alpha beta u. Sorry, I need to like hurry because it's already 50. And 10, 1 times u is equal to u. Okay, perfect. So, okay, so we have this, and then the elements in V are then called vectors. Okay. So now the elements in V are called vectors. Okay, so this is now what it means to be a vector. If you have a set with addition and multiplication that satisfies all these, then the elements in this set V are called vectors now. And again, now that doesn't restrict us completely to the same ones that you've always been with the arrows. These can be anything. As you can take, I don't know, your favorite set of whatever. If you define addition and multiplication in the correct way, those things will be considered vectors. Like in quantum physics, right? So states of a system, using those bra and ket notation, those become vectors under the addition multiplication that you define there. So they don't always have to just be arrows, and they can be literally whatever you want. Okay, so we'll call it a day there. No challenge question next this time, but next time there will be. Yeah, so. No questions, comments, concerns? Okay.